Hi, everyone. Let's continue our journey of talking about the stars and what we're after, what stellar property we're after in this video is going to be getting towards how bright a star is. Whenever I say how bright a star is, I'm really talking about the star's luminosity. How much energy is it giving off every second? And just like we talked about with the sun, if we know how bright a star is, how much energy is giving off every second, what is its luminosity? Then we also know something about what's going on in the core of that star. We know something about the nuclear reactions that are producing that amount of energy, that level of luminosity. So in this video, the property that we're after is the luminosity of stars. However, we don't observe the luminosity of the stars directly. We just see how bright stars appear to be. So how bright something appears to be is connected to how far away it is. And this is a fairly simple concept. If I had two light bulbs, each one 100 watts, and I held one that was say 10 feet away from you, you'd go, dang, that's a bright light. If I took the other one and I moved to be 100 feet away from you, you could look at that light and it wouldn't be as bright. As something moves farther and farther and farther away, less of that light reaches your eye, spread out over a larger area, and therefore it appears dimmer. This is very similar to when we talked about the solar constant. If we were to go stand or be right next to the sun, you couldn't look at it. It would be way too bright. Even from here at Earth, the sun is incredibly bright. And if you move all the way to the edge of the solar system, the sun is still pretty bright, but it's much, 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 much dimmer. I mean, we can look at stars in the sky without hurting our eye, right? That's because they're dim enough for us to actually see them. They don't light up the night. The sun, however, lights up the day because it's much closer. Therefore, it appears much, much brighter. Okay, so clearly there's a connection between distance and how bright something appears. And that's what I'm trying to show you on this image. It's where we'll begin and where we'll end in this video. So here I have a space-based view and then an Earth-based view. We have our favorite cartoon Galileo that's outside looking at these two stars, Star Triand and Star Svak. To them, he looks out at them. He can measure their brightness as they appear for him. And he goes, huh, those two stars have the same brightness. However, if you were to actually look at where these stars are in space, know their distance that you could determine using parallax, then you might notice that star Svak is much closer. Say it is at a distance of 25 light years away from the Earth. And you can use a parallax measure to figure out that star Cheyenne is 50 light years away from the Earth, 2 times farther away. And let's just assume that we know the properties of the star. So this star would have say its luminosity is 25 times greater than the sun. For these two stars to appear the same brightness, this one would have to be 4 times brighter, 100 times the luminosity of the sun. So it's 2 times farther away. So it's getting dimmed by a factor of 2 squared, 4. So it appears like it's the same brightness as the closer one. That's what we're going to be talking about in this video, is how we can start looking at these things to tell, like, hey, here we have two stars. One is naturally incredibly bright, 4 times the luminosity, but because it's 2 times farther away than this star over here, then it appears the same brightness in the sky. And this is just highlighting that there is this connection of brightness and distance, of how bright something appears is connected to how far away it is. So two stars can have different distances and appear to be the same brightnesses if one is just naturally a lot brighter than the other. Or the farther one is naturally brighter than the other. Okay, so let's start learning some of this terminology. We have to really keep track of how things appear versus how they truly are. An absolute, how it truly is, versus an apparent, how things appear to be. Oh, wow. Okay, we'll just start from here. Apparently my animations on these past videos are going a little bit crazy. So absolute brightness. This is a term that we're going to use to refer how bright a star truly is. And when we're talking about the stars, how bright a star truly is comes down to how much energy it's giving off every second. So absolute brightness is a star's luminosity. This is what we're after. We want to know how bright a star naturally is. That's plentiful information. It is a property that belongs to that star independent of other things like distance. It is what we call an intrinsic property of the star. So absolute brightness for a star is the luminosity. And it's a very, very valuable thing to know because it tells us a lot of things about the star, including something about the nuclear reaction rates in its core. When we're talking about absolute brightness for the stars, when we're talking about the luminosities of stars, as I had mentioned previously in the sun material, that we measure the brightness of stars in terms of how bright the sun is, a number of solar luminosities, where the sun itself has one solar luminosity, which we label as L with a subscript of sun. So to talk about the luminosities of stars, what we'd do is we'd say something like, oh, well, that star over there has a luminosity of 21 solar luminosities, 21 L sun. And I know that that means that star is naturally, intrinsically, absolutely 21 times brighter than the sun. It's giving off 21 times the amount of energy that the sun is. A star with a luminosity of 0.05 solar luminosities, that equals 1/120th solar of a solar luminosity, is naturally going to be 20 times fainter, 20 times dimmer, 5% as bright as the sun is. So 0.05 solar luminosities is a naturally dimmer star. It is less bright, 20 times dimmer. And this is not what we directly observe, which is what I was trying to show you with that image. What we actually see from Earth is how bright they appear to be given how far away they are. So when we're talking about the apparent brightness, how bright a star appears to be, it's a combination of not only how bright it naturally is, but how far away it is. So it's a combination of how close or how bright the light bulb is, how bright that light bulb is going to appear to you, depends on not only how bright it naturally is, but how far away it is. A light bulb viewed from 1,000 feet away is not very bright. A light bulb right in your face is very, very bright. So apparent brightness is a combination of absolute brightness and distance. And we just need to understand that relationship because if we can go outside and look at a star and go, hey, that star appears to be that bright, whatever it is. We can measure an apparent brightness. If we can determine the distance then, and we know how distance relates to apparent brightness, then we could use the distance to go from apparent brightness to absolute brightness. To go outside and look at a star and go, oh, you appear to be that bright. And your distance, say from stellar parallax measurement, then we can use the distance go, well, if you appear to be that bright and you're that far away, you must have a luminosity of whatever. And then we've determined the luminosity of a star. Told you that distance thing was the foundational step. So there is a connection between how bright something appears, its apparent brightness, and its distance. We just now need to understand that. So again, just because we're learning new terms here, it's good to say them multiple times. Apparent brightness is how bright a star appears to be. It's not how bright it naturally is, intrinsically is. It's how bright it appears to be, which depends on how far away it is, its distance. So apparent brightness depends on the distance to a star. And this is the same thing as saying, it's as simple as saying, things that are farther away appear dimmer. If I take a light bulb and I move it farther away from you, it does not look as bright to your eye. So given two stars that have the same luminosity, the same wattage, the same amount of energy given off every second, the one that is closer will appear brighter. The one farther away will appear dimmer. That is pretty much a simple statement. The apparent brightness is inversely proportional to the square of the distance. And this is just like whenever we talked about going from the solar constant to the solar luminosity. We measured The solar constant is an apparent brightness measurement. It told us how bright the sun appears to be at a distance of 1 astronomical unit away. Now, light was spreading out over the surface of a sphere that had a radius of 1 astronomical unit. All that light that left the sun in that 1 second pulse went out and got diluted, spread out more and more over this entire sphere as the radius increased to 1 astronomical unit. And since it's getting dimmer, it's spreading out, it's diluting itself over the surface of that sphere, and that sphere is getting bigger as time goes on, then we can naturally see that the brightness will get less with increasing distance, and that light is spreading out over the surface area of a sphere, which a surface area of a sphere depends on the size of the sphere, the radius of the sphere squared. So as you move farther and farther and farther away from something, the brightness will get dimmer with the distance squared. The apparent brightness is inversely proportional to the square of the distance. Inversely proportional to the square of the distance. Oh, we've gone over this before. That's an inverse square law. Brightness is an inverse square law. Brightness is inversely proportional to the square of the distance. And we observe the apparent brightness from Earth, but we want to know how bright a star truly is. We want to know its luminosity. So all we really need to do is to connect apparent brightness to luminosity is really know the distance. And now that we know that brightness falls off, it gets dimmer as 1 over the distance squared. Double the distance and it'll look 4 times dimmer. Triple the distance, it'll look 9 times dimmer. 10 times the distance, that object will now appear to be 100 times dimmer, 1/100th as bright. Now that we know that relationship, all we have to do is measure the apparent brightness, figure out what the distance is, and then apply how brightness changes with distance to actually translate that into a absolute brightness. All right, now I know inverse square laws don't come naturally. Well, actually, they do come really naturally. They appear all over in nature. Did not mean to make that joke, but once I said it, I had to do it. Okay, they can be hard to understand at first. So let's explore and relook at apparent brightness is inversely proportional to the square of the distance. So if I have a light bulb and I move it to be 2 times farther away from me, it'll appear 2 squared, 4 times dimmer, 1/4 the brightness. If I move it to be 5 times the distance away from me, it'll look 5 squared, 25 times dimmer, 1/25th the brightness. Because it's 1 over the distance squared, 1 over 5 squared is 1 over 25, 1/25th as bright. Same thing as saying 25 times dimmer. Okay, hopefully saying that in all the various ways that can possibly be said, those are starting to sound relatively familiar to you at this point in the semester. Let's talk about a few examples though. So given 2 stars that have the same absolute brightness, they appear to be the same brightness, they have the same wattage, they're both 100-watt light bulbs, except stars, so we're talking like 10 to the 26-watt light bulbs. So if one star is going to be 10 times farther away than the other star, I want to know how will their brightnesses compare? How will their apparent brightnesses viewed from Earth compare to one another? They're naturally the same brightness, but one is 10 times farther away. Apparent brightness drops off as 1 over the distance squared. It's an inverse square law. So 10 times farther away, 10 squared is 100. It'll appear 100 times dimmer. It'll have 1/100th the apparent brightness. That's pretty dim. So 10 times farther away, it'll appear 100 times dimmer, which is the same as saying 1/100th the brightness, 0.01 times as bright. Okay, so if one star, and I wanted to just pick a bigger number that's not easy to do in the head, just to show you that you just have to punch numbers into your calculator. So if one star is 35 times closer to the Earth than the other, so I want to know how much brighter is the closer one. Well, it's closer, so it appears brighter. How many, how much brighter? Well, as it gets closer, its brightness is going to increase with the distance squared. So it's closer, 1/35th the distance. So the distance went down by a factor of 35, which means the brightness will go up by a factor of 35 squared. 35 squared is 1,225 times brighter. And now I can talk about this image to try to be a little cyclical about what I'm talking about here. So here we have a light source, a star. And here we have these surfaces of, imagine a 1 second light pulse going out. So that light spreads out as a spherical surface. At time 1, it would have a spherical surface of this size, this inner one. And what we're going to do is we're just going to look at how much light is going through some square, some set cross section. So maybe this is the light that's hitting your face. So here it's spread out over 1 square. We double the distance. Now we have a much bigger sphere. And that 1 square, just moving forward, would now be 4 squares. So double the distance. 2 squared is 4. Light spread out over 4 times as much area there. So each square would appear to be 1/4 the brightness. And then spread out at time 3. Now it's spread out over this giant sphere. And what was 1 square that became 2 squares at 3 times the distance? That same amount of light that was going through the 1 square is now is spread out over 9 squares. So each one of those squares would appear 1/9 as bright. It contains 1/9 the light that passed through this square right here. All right. So hopefully you've made that connection about that apparent brightness is an inverse square law. Because now we're going to start playing around with this, because what can we do? We can go outside, we can look and see how bright the stars are. We can measure that at a telescope. That's our apparent brightness. We can measure the distance by using parallax. And this is going to allow us to get an intrinsic property of a star. That's what we're after. We want to be able to look out at the night sky and start looking at all the stars and say something about their properties, their intrinsic properties. And the intrinsic property we're after here is luminosity, how bright it is in an absolute sense. Okay, so we've already connected that apparent brightness is inversely proportional to the distance squared. How does how bright something appears relate to its absolute brightness? How does it relate to its luminosity? And this is as simple as proportionalities get. They are directly proportional to one another. How bright a star appears is directly proportional to the luminosity. A larger luminosity means that the star is naturally brighter, it'll appear brighter. A smaller luminosity means the star is naturally dimmer, it'll appear dimmer. If we have 2 stars at the same distance, one has a high luminosity, one has a low luminosity, the high luminosity one appears brighter. Okay, so apparent brightness is directly proportional to the luminosity. It's inversely proportional to the distance squared. So now I have this nice relationship that's connecting everything that I need. The apparent brightness is proportional to the luminosity and inversely proportional to the distance squared. I can determine the distance, I can determine the apparent brightness, which is going to allow me to reason out, to calculate the luminosity. Okay, so just to show you how simple the luminosity, this directly proportional, apparent brightness is directly proportional to luminosity. This is almost going to sound tautological to go through, but let's just go ahead and do it. So given 2 stars that are the same distance away, say 10 light years away or something like that, 10 parsecs away, how many times naturally brighter is one star compared to another? Or I'll give you how many times brighter one star is compared to another. And then the question is going to be, how many times brighter will that star appear? So if we compare a star that has 9 times the luminosity of the sun, a 9 solar luminosity star, compared to a 1 solar luminosity star, then the 9 solar luminosity star will appear to be 9 times brighter than the 1 luminosity star if those stars are at the same distance. It's that simple. 9 times naturally brighter, same distance away, it's going to look to you 9 times brighter. a 100-watt light bulb next to a 10-watt light bulb. They're equal distances away. The 100-watt light bulb will look 10 times brighter than the 10-watt light bulb. We compare a tenth of a solar luminosity, zero point 0.1 solar luminosity star to a 1 solar luminosity star, and they're the same distance away, then the zero point 0.1 luminosity star will appear to be 1/10 as bright, which is the same as saying 10 times dimmer. So that part is pretty simple. But I wanted to go through each one of these so then we can deal with them independently and then compare how the two factors are playing off one another, luminosity and the distance. So now we're going to put it all together. Because when we're considering how bright two stars are going to appear, their apparent brightnesses when viewed from Earth, if we want to know how bright two different stars will appear given their luminosity and their distance, then we can reason that out. So we can reason out the apparent brightness, how bright one star will appear compared to another star, playing around with their distances and their luminosities. And this exercise that we're going through is not quite how we do it in astronomy, but it really helps you get how all of this works, how all of this interweaves. So in another video, I'm going to run through several examples of how you can determine whether one star will appear brighter or dimmer than another star whenever I give you the star's luminosities and solar luminosities and their distances or their ratio of their distances. How many times farther away is one star compared to another star? We'll get there. I'm going to save that for another video. But with this video, let's just run through a simple example and wrap things up as we begin. So I want to give an example of the interplay between apparent brightness, absolute brightness, luminosity, and distance. So let's consider two stars. Star 1 is going to have a luminosity 100 times that of the sun. It's going to naturally be 100 times brighter than the sun. And yes, there are stars out there that are that bright. There are stars out there that are much, 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 much naturally brighter than 100 times that of the sun. And then let's consider another star, star 2. That's a luminosity 25 times that of the sun. And let's say that these two stars are not at the same distance away. Star 1 is 2 times farther away than star 2. Okay, I can deal with that. The 2 times, let's do with the distance first. 2 times farther away means that it's going to appear 4 times dimmer than if I move it away. So imagine that they're at the same distance. And if I move this one away to be 2 times farther away, it'll dim by a factor of 2 squared, 4. So it'll dim by a factor of 4. This is what I'm going to end up calling the dimming factor. So it's going to appear 4 times dimmer based on the distance. However, it's appearing 4 times dimmer based on the distance, but it's naturally 4 times brighter. So it naturally appears 4 times brighter, and the distance, the fact that it's 2 times further away, making it appear 4 times dimmer, those balance out. So in this case, these two stars, even though one is naturally 4 times brighter than the other, the fact that it's twice as far away makes it appear dimmer, 4 times dimmer. So these two stars in the sky would have the same apparent brightness. Which brings me back to where we began. Here we have Galileo observing star Cheyenne and star Svak. Star Svak has a luminosity 25, natural brightness is 25 times the luminosity of the sun. It's at 25 light years away from the Earth. Star Cheyenne is 2 times farther away at a distance of 50 light years away. So 2 times 25 is 50. And it has a natural brightness, a luminosity, an absolute brightness of 100 times that of the sun. But because it's 2 times farther away, means that farther away it's going to appear dimmer. 2 times farther away tells me it's going to appear 4 times. It's going to be dimmed by a factor of 4. So we got to compare how much it's being dimmed by distance to how many times it's naturally brighter. So 100 is 4 times greater than 25. So it's naturally 4 times brighter, but it's 2 times farther away, which means that it's getting dimmed by a factor of 4 compared to this one. And those two balance out, so they have the same apparent brightness. There will be several exercises that we'll go through in another video. And yes, there will be quiz questions about this. There will be exam questions and homework questions, because this is really piecing together so many parts of the class to connect and to understand how we can actually go from measurements of apparent brightness and measurements of parallax to get distance to actually tell something true about the star, its luminosity. So yes, this exercise will feel difficult at first for many of you, but it's worth going through this because you are literally going to be figuring out properties of stars. And you'll understand that we can get those properties with just a few simple measurements at a telescope. Thank you for tuning in for this video. I will see you in the example video.